All right, if I get your attention up front, we are starting on our first set of notes for Unit 2. The first thing we're going to do is label our two variables. Variables come in two flavors in statistics. We have explanatory variables, and we have response variables. Can I get a thumbs up if you have heard of those before, and a thumbs down if you have not? And I see one thumb up and a whole lot of thumbs down. And the thumb sideways, like it kind of sounds vaguely familiar. Yeah. So you probably have referred to these more commonly as independent and dependent variables. Independent, I know how to spell. Those are the more common terms used when you're talking about traditional math classes or when you're hanging out in like a science class. Yeah? They serve the same purpose in statistics, but explanatory and response is a more descriptive way of labeling them in terms of what they do and how they behave in statistical studies. So that's why the name changed. Explanatory variables are the variables that the statistical researcher controls or manipulates. They're the ones I'm in charge of. Oftentimes, the explanatory variable is the variable based on how I decided to group my sample for comparison, right? I group them by gender. I group them by age, right? I group them by income levels. That would be my explanatory variable. And I'm going to compare across those groups for a response to something else. Change in diet, yeah, new medication versus placebo, that kind of thing. Yeah. So explanatory is the thing I control, or it's the groups that I'm putting people into. The response is the thing I'm interested in measuring as a result. You can often think of it as the explanatory explains what happens to the result. And oftentimes, particularly when we're talking about studies involving humans, it'll make sense that the explanatory explains what we see in the response. The reverse won't be true. Human studies are typically very clearly one way. Yeah. We're going to practice identifying with a couple examples so we can see what it looks like. Yeah. All right, so first example says Yellowstone National Park staff surveyed a random sample of 1526 winter visitors to the park. They asked each person whether they belonged to an environmental club like the Sierra Club. Respondents were then also asked if they owned, rented, or never had used a snowmobile. Don't judge me. The results of this survey are shown below. Identify the explanatory and response variables in the study and explain your reasoning. So first thing we do is we look at the table they gave us and identify the two variables. So what are the two variables involved in this study? Yes or no, which belong to, very good, environmental club membership. So that's the variable, and then the categories in that variable are yes and no. Good. And then my other variable, snowmobile usage. Go. We want to decide which one is which. So of those two variables, which one sounds like it is groupings of people that the researcher put the people into, and which one sounds like the response I am interested in measuring? So take a minute, discuss with your neighbors which one is the grouping of humans, which one is the response that I'm interested in measuring. Yeah, give you about 60 seconds. That doesn't look like statistics. Have we talked to Ashley at any point? Okay. Don't let them ignore you. You can kick them under the table if they're ignoring you. Yes. And then which one would be like the data we're trying to find? Right. Which one is the groupings of humans? Which one is the data we're collecting from those humans? Okay, show of hands who can tell me what the explanatory variable is. Yes, Drew. Environmental club membership is the explanatory. Can somebody other than Drew tell me why this might be the explanatory? Preferably somebody who hasn't spoken yet. I'm standing over here because this side of the room is traditionally pretty quiet. Thoughts? No thoughts? Frowny face. Did anybody else decide that was explanatory, Bailey? What do you got? Yeah, that is a category that I have decided to separate my sample into. Do they belong to a club or don't they? I have artificially created two groups from a single population, taking the population, dividing them into environmental club, no environmental club. That was a me decision, which means the other guy is our response variable. Very good. Once we've divided them into groups, environmental club and not environmental club, we ask them about their snowmobile usage, giving them 3 choices. And then we're looking for a relationship. Does knowing that they're a member of an environmental club give me information about the likelihood that they own or use a snowmobile? Good. Try another one. Next one, same process. Identify the explanatory and response variables. If possible, explain your reasoning. A says heart rate and whether they are an active member of a gym for a sample of adults. Give you about 30 seconds to process. Did you fill out any hall pass? All right. Who's got a vote for what our explanatory variable is? Please don't make me get the name generator out. Ivan? So Ivan says that active membership at a gym is our explanatory. Can I get a thumbs up if you agree? I see thumbs up popping around the room. Somebody other than Ivan, how do we know that that's our explanatory? Drew.
It's whether or not you're an active member of the gym is a group setting.
Very good. And I see nodding from several people around the room that we agree. That's a grouping of people. Very good. So this is how we're grouping, which means what is my response? Heart rate. I'm measuring heart rate. Good. And I'm going to use those shortened terms because I'm tired of writing words all day. It's been a long day. Very good. Next one. Same idea, explanatory and response explain. the price and square footage of living space for a sample of houses for sale. Give you about 30 seconds to talk with your neighbors. Don't judge me. I know. I feel you. Yeah. It's. You've been here since when? Yeah. See, we're all tired. I feel your pain. That was an impressive eye roll there. Excuse me. All right, I hear some vaguely off-topic conversation, so that implies we've answered the question. Bailey has a really good. What does Bailey say? Now that you've been thrown under the bus. So Bailey says price relies on square footage. So which one is the explanatory in that case? We're going to talk about it. It's not wrong, but we're going to talk about it because I want to see if anybody else said something different. Did you say something different? What did your table say, Jennifer? The explanatory? So Jennifer's group said square footage was explanatory and price was the response. So, is there a grouping of people involved in example 2b? No, there were no humans involved in this discussion. We're not grouping humans by any categories. These are two variables that could conceivably go either way. So this is an example where both of those answers are correct. This study, we would need more details about what question was being asked. Yeah? This could be either, because there was no grouping of humans for comparison. And that usually is our big clue for how to do this. So if we're not grouping humans, it gets a little harder to tell the difference, and sometimes it doesn't matter. Yeah. Good. Very good. You will notice that in a lot of examples where we're talking about explanatory and response variables, more often than not, the response is the variable given first. So if you're reading a word problem and you're unsure, more often than not, the response variable is going to be given in the word problem before the explanatory. It's not 100% the case. You can word English phrases in lots of different orders, but more often than not, response comes first because that is the quantity we're ultimately interested in measuring. Okay, questions on explanatory and response variables? Yes. So in that case, you would need to state why you can interpret it one way or the other. Why it, yeah. You need to provide some context or some explanation as to why you thought it was that way. For B, because that was a good question, either answer would get credit as long as you explained your why. Why did you pick this reason over that answer? Yeah. As long as there's an explanation to support, you'll get credit. Okay, so now that we've labeled our variables, we're going to start the summarizing, displaying, describing process. Yeah. And we summarize two categorical variables in tables called two-way tables, which we saw in the warm-up today. Yay. Sometimes these guys are also called contingency tables. Those two phrases mean the same thing. One of your categorical variable labels is across the top, one is down the side, and you end up with intersecting rows and columns. Yeah. We are going to see these again in second semester when we start looking at statistical inference, because we're going to learn how to check whether there is enough statistical evidence to support a relationship between two categorical variables, and we will do that by analyzing those two-way tables. So these will come back around again in second semester. Yeah. Okay, so two-way tables are almost always tables of counts, also called what? Frequency. Very good. These are usually tables filled with frequencies. On rare occasion, you will see a crazy statistician who will fill them with relative frequencies. What is a relative frequency? A percentage or a proportion. Very good. Very good. These tables are used to summarize the relationship between two categorical variables. There is a lot of extraneous chatter in the back of the room, and considering so many of us have been here since 5, I'm a little surprised we have the energy for it. Frowny face. So when we do two-way tables, we're going to do calculations with them to analyze the relationship between the two variables. It is most often useful to have the row and column totals built into the table. So if you are asked to construct a two-way table, you should include a total for the rows and totals for the columns. We're going to do that for our environmental club membership table. Yay. And the reason we do this is because we can use the values in this table to then calculate proportions or percentages, which are then used to answer probability questions. Yay. Which is Unit 4, which is upcoming. So really quick, we'll see how fast I can do math. That's going to be 6, 5, 7. That's going to be a 4, carry the 1, a 7, 5. That's going to be 2, 9, 5, assuming I can do math in my head. Yes, I can. Good. 15, 26. 1, 2, 2, 1. And 3, 0, 5, because I've already done this once today. In that additional data that I've added to the edges of the table, also known as the margins of the table, what does this box in the bottom right-hand corner represent? The grand total, yeah, the total, also known as our sample size. You are going to be referring to it oftentimes as the table total when we start writing formulas for how to calculate things from a two-way table. But that bottom right corner is the total of all of the data in the table. It should be the same as your sample size. Yes? That is the lowercase n variable. Yes, very good. That should be equal to whatever you were told in the problem was the number of people in your sample or the number of objects in your sample if we weren't interviewing people. Yeah, very good. And we are calculating several relative frequencies, also known as percentages or proportions. Relative frequencies come in multiple flavors. We're going to talk about 3. I'll show you how to calculate them from the table, and then we're going to do an example so you can see what it looks like when we do the math. Yeah. Okay. So first, the proportion or percentage of individuals that have a specific value for one of the categorical variables, meaning I am focusing on just one variable, one category in that variable. That is one of my rows or one of my columns. That is called a marginal relative frequency. And it is called a marginal relative frequency because the top of that fraction that we're going to use to calculate our relative frequency comes from the margins of the table. It is either a column total or a row total, because I am looking at the sum total for one of my categories, which is a row or column. So to calculate, we build our fraction. The top is one of those marginal counts, so a row or a column total. The bottom of that ratio is then the table total. For example, if I wanted the proportion of snowmobile ownership, come on. That's a single category, yeah? Just who owns a snowmobile. In my table, that's the owns snowmobile row. So to calculate the percentage of snowmobile ownership, I'm going to take the total for the owns row, which is 295, and I'm going to divide it by my table total, my sample size, 1526. That is going to give me a decimal. How do I turn it into a percent? Very good. Times 100. Perfect, perfect. Somebody with a calculator. What do we get when we do that? 19.3. So of those 1,526 people that we surveyed, 19.3% of them own a snowmobile, which is a really high percentage. This must be living somewhere where there's lots of snow. That seems like an oddly high percentage of people who own a snowmobile. I heard a wait in the back. Are we good? Yes? No? Yes? Okay. All right, next one is the percentage or proportion of individuals that have a specific value for both of the variables, meaning I'm in a specific row and a specific column. Where those two intersect, that's the count I want. This is the intersection of a row and a column, and it is called a joint relative frequency. There is a key word that you should keep an eye out for questions that are asking for a joint relative frequency. Because we are looking at the intersection of a row and a column. I am looking for somebody who both owns a snowmobile and is a member of the club. You should probably see somewhere in that problem an and statement. Variable 1 and variable 2. Yeah, they should mention both. That's a clue, it's a joint. To calculate it, we're going to find that single cell that's located at the intersection. And we're going to divide it by the table total. So this is one box out of the table divided by the sample size. Next one is the weird one. And the last one is called a conditional relative frequency. And what a conditional relative frequency does is instead of looking at my whole sample, I am looking only at one category of one of the variables and ignoring the rest of the table. So this changes the denominator. I am limited to one category of the table. I am only looking at one row or one column, meaning the bottom of my fraction instead of the table total is now the row total or the column total. Yeah. So conditional relative frequencies are going to be a single cell value, one box in the table, divided by the row or the column total, whatever I'm limited to. Whatever row or column I'm limited to, whatever's determining the denominator of my percent or proportion fraction, is called a condition. Give me 1 second, Catherine. Which is why this is called a conditional. What was your question? To what? Huh? Oh, no, it does not. It's tangent is a ratio, and so you're going to see some similarities in structure, but completely different concept in terms of sine and cos and tangent are not tied to reality in quite the same way that these are. And those of you who are also taking my pre-cal class will get to see lots of trig functions next semester when we get to trig. Yay. So what I'd like to do is I'd like to introduce that keyword before we move on and then do some examples with some data so we can get some practice. Much like joint probabilities have the keyword and, when you are given a condition, they are going to use the keyword of. I want the proportion of snowmobile owners who are also club members. Whatever comes after the of, that's your condition. That is 99.9% of the time what that wording is going to look like. So what proportion of whatever comes after that of, that's your condition. That's the bottom of your fraction. Yeah. So let's try it out with some actual data. So the table we're looking at is information on songs released in the US by the Beatles. They have had more #1 songs on the Billboard Hot 100 than any other artist or band in the US. And this particular table groups the songs into two categories. Were they in the top 100? Did they reach number one? Or did they not reach number one? And then they were sorted by artist. Who wrote the song? And then they list the band members, and then there's multiple writers as their last category. So who wrote the song? Did it reach number one? Yeah. We're going to answer some questions. I'm going to color code this, so you may want to have some markers or colored pens handy. Otherwise, I lose track of what I'm doing. So we'll start with our first question, which says, what percentage of Beatles songs reached number one? How many categories are mentioned in that question? What are the two? Ooh. I'm gonna underline this one. Is Beatles songs the category in that table? Yeah, it's all of our sample. Good. So there's one category. Beatles is like all of the songs are Beatles. So the category is the songs that reach number one. This is one category question, meaning this is a marginal relative frequency. So one category means marginal. Yeah. And I'm going to go up to the table and figure out where the data values I want for this marginal relative frequency lie. So it says songs that reach number one. That's my yes row. So I want the yes total, which is 19. So for this guy, I'm going to do 19 out of, and how many total songs did we sample? Perfect, 205. So 19 number ones out of 205 total songs, and they said they want a percentage answer. What else should I do? Yes, we are on fire today. Very good. Glitchy today, that's what we are. And when I did that this morning, I got 9.3%. And you should check my math and make sure that I was not losing my mind after 3 hours of sleep. Just rounded. Are we okay with that? You see some nodding? Good. Okay, let's do the next one in blue. Next one says, what proportion of Beatles songs were written by Paul McCartney and reached number one? What keyword is in that statement, Yari? Oh, no. And there's an and right there, which means this is a joint marginal frequency. The keyword and is telling me it's joint. Yeah. So in the table, I need to find the cell that is both written by Paul McCartney and reached number one. It's a single cell in my table. So I'm going to go to the Paul McCartney column, which is the middle column. So I'm here. And then I'm looking for the reached number one row, which is here. And they intersect at 12. Yeah. So 12 out of how many Beatles songs? Yes. Very good. This one said proportion, so I'm going to leave it as a decimal. And I got 0.059. And somebody with a calculator, again, should check my math. Good. Very good. Figure out what type of relative frequency it is. Look in the table for where you're supposed to be. Good. Next one. I need a different color. Let's go pink. Pink is a good color. What percentage of Paul McCartney songs reached number one? What percentage of Paul McCartney songs reached number one? Amy, what keyword is in that phrase that I'm looking at? The keyword here. Of. Yeah. Specifically, it says of Paul McCartney songs. Yeah. So this is a conditional relative frequency. The condition is the section of the table I'm limited to. So my condition is Paul McCartney. That's what came after the of. So I am only looking here. This is the only part of the table that exists now for me. In that column, how many reached number one? 12. We already saw that. Out of how many total Paul McCartney songs? 75. Good. And this one asks for a percentage, so I'm going to take that and multiply it by 100. And I'm pretty sure you get a nice, pretty whole number. Yeah. Of all the songs, 9.3% reached number one. If I'm only looking at songs written by Paul McCartney, 16% reached number one. Tells me maybe Paul McCartney had an edge in his writing skills when it comes to music, yeah? Is that a question or a hair? A hair? Okay. Last one. We're going to try it again. Orange is good. For D, it says, what proportion of number one songs were written by Paul McCartney? Jaden, what keyword do we see in that question? Of, proportion of, very good. And specifically of number one songs. I am now limited to the number one song row of the table. Only this exists for me now. I am in the number one song row. Of the number one songs, how many were written by Paul McCartney? 12. The numerator is the same as the question in C. What's going to be different? Number on the bottom, the denominator, good. The total number of number one songs was 19, yeah. And I got 632 rounded, about 63.2%. I see nodding. Yeah. So of all of those number one songs, 63.2%, more than half of the number one songs, were written by Paul McCartney. Slightly more impressive when phrased that way. So, reminders. When you are doing proportion questions from a two-way table, look carefully at the number of categories that were mentioned, because if it's only one category, it's automatically a marginal. If there are two categories mentioned, is it joint or conditional, and or of? Yeah? Good. Questions on two-way tables? No. We're going to see these again and again. You're going to get lots of practice with them. The last thing I'd like to do today is dip our toes into the graphing, displaying two variables in a graph. And we'll finish it either Friday or Monday, because we're not going to finish it today. I know. It's long. Deep breath. We got this. Oops, I didn't mean to do that. All right. So let's go down here. We are going to talk about three types of graphs that display two categorical variables, right? We're talking about categories. You may. Thank you for asking. The first one you already did today. You did a side-by-side bar graph in our bell ringer. One variable is along the x. We treat that as categories. One variable is along the y. We split it by percents or by counts. 2 bars next to each other, yeah? The nice thing about side-by-side bar graphs is we didn't have to do any additional math to draw the picture. We just used the two-way table as it was given to us. That's nice, because as mathematicians, we are lazy. The other two graphs we're going to talk about require a little bit of prep work. A little bit. Yeah. The next one we're going to talk about, the one we'll do today, is called a segmented bar graph. Kind of related by side by side, but instead of having the counts next to each other, I'm going to have percents stacked on top of each other. So I'm going to take a bar for one category and divide its area by percent of the other categories. You can see an example here in the middle. This middle graph is the example of a segmented bar graph. And if you look along the bottom, it's been sorted by no, I'm not a member of a club, and yes, I am a member of a club. It's been sorted by the explanatory. On the y-axis is percent, and that percent has been grouped by snowmobile usage, which was our response variable. What do you notice about the heights of the bars in the segmented bar graph? Yeah, they're all the same height. They reach all the way to the top. Because if I look at a single variable, right, in a single category within that variable, it should all be 100%, right? This bar should represent all of the no's. That's 100% of the no's. How those no's were distributed against snowmobile usage is where the segments come from. Yeah. The last type of graph, the one we'll talk about next time, is called a mosaic plot, which is this last example here on the right. Similarities between segmented and mosaic, what do we see? Jade. Very good. Both of them go all the way up to 100. We have bar up to 100, bar up to 100 for both. Good. Any other similarities? Yes, Katie? Good. If I read across, the percentage here for the no's who never used a snowmobile is the same as the percentage here for the no's who never used a snowmobile. Those segments are the same height for each category. Yeah. How are they different? Yeah, now the width matters. Now the width matters. Segmented, we're doing the same traditional bar graph where all the bars are the same width. Now we're taking width into account, and that width is giving us proportion of no's versus yeses in terms of the breakdown of our original sample. So now I'm getting information in both directions instead of just one direction. Mosaic plots give us the most information about the data. They are also the ones that take the most work to draw, which is why they are the least common in terms of statistical plots that you see in media. This side-by-side bar graph, Excel and Google Sheets can do really quickly and does really well. The segmented, most spreadsheet programs are pretty good at. You get to mosaics, yeah. On the AP exam, you can expect you may, on an FRQ, be asked to sketch a quick side-by-side, just like we did for the warm-up today. Yeah. Not likely, but possible that you might be asked to do a segmented. It is very, 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 very unlikely that they would ask you to do a mosaic. The big thing with mosaic plots is that you understand how to read them and that you understand the width has meaning and the height has meaning. So now I have to consider two directions and not just one. Yeah? We're going to do a segmented bar graph together. We're going to talk about how to do it and then do one for some data. And then we'll stop for today. I'll give you a little bit of time to work on your projects. And then we'll pick up where we left off next time. Okay, let's get to our step list. Segmented bar graphs. I wrote it down so I wouldn't forget. If I go back to the previous slide, you'll notice on all of those x-axes, it was the explanatory variable, the groupings of people. Yes, I'm in a club. No, I'm not. So the very first thing I want to do is sort out which variable is which. So identify your variables. It is good practice to put the explanatory variable on the x and the response variable on the y. When we start doing numeric paired data later, we will also stick with this rule: explanatory on the x, response on the y. You saw this in science and math class: independent on the x, dependent on the y. Same rules here. Yeah? After I've identified my variables, next thing I'm going to do is draw and label my axes. So horizontal axis, vertical axis, slap those variable names on there, right? Before I can start plotting data in that graph, what else do I need to do to my axes? I've got labels. The what? The width. I need some numbers on there, some scales. Yeah, put those tick marks on there. Good. Scale both of your axes. On the x-axis, right, that's going to depend on which type of graph you're drawing. For segmented, because it looks like a bar graph, you have a width for your first category, a space, a width for your second category, a space, right? Because bars should not touch in bar charts. Okay? On the y, we should scale from 0 to 100 because we're plotting percentages for the segmented stacking. So x-axis is just the names of the bars, y-axis is percentage. Good. Next one, we're going to draw the 100% bars. We're going to do it for every category because we know for segmented and mosaic, they all go up to 100. So just start at 100 and then we'll break it down from there. So far, we haven't done anything we haven't already done in other graphs. Step 5 is the new step. This is where we're going to do some math. We're going to segment the bars. And you will notice there is some direction there. It says calculate the relative frequency for each category of the response variable for each category of the explanatory. We are doing conditionals. I am looking at the breakdown of snowmobile ownership for just the no's. Those conditionals where no is the condition. And then I'm looking at snowmobile ownership for just the yeses. That's another conditional where yes is the condition. So when I'm doing these relative frequencies, I should be using a row or column total and not my sample size as the bottom of my fractions. Yeah. That's the hard part. That's the part that's going to take practice. Once that's done, I just need to write a key. Yeah. We need to color code them just like we did for the side-by-sides for our warm-up. college students need to stop sending me emails. Okay, let's do an example. All right, so this data here is the data from the Golden State Warriors question that we saw during our bell ringer, where we looked at the percentage of wins and losses as a function of how much rest they got before the game. None, 1 day, more than 1 day. Yeah. And we didn't decide anything. We need to decide on our explanatory and our response variables for step 1. So my first step is the amount of rest, the explanatory, or the outcome of the game, the explanatory. It's kind of obvious because it's in the name of the variables this time. Ooh. My vote would be this and this, because remember, response is the outcome of interest that I'm measuring. Outcome was in the name of the variable, so easy to identify as the response. Next step, what do I do? What was step 2? Yes. Draw and label the axes. My axes are drawn because I was in a good mood when I put these notes together. So I just need to label them. Explanatory on the X, response on the Y. So amount of rest and outcome of game. Come on. Could we cooperate today? There we go. We did it again. All right, Sophia. I drew my axes. I labeled my axes. What's step 3? Very good. Slap some numbers and some tick marks on them. Good. So in this case, I'm going to make a bar 4 chunks wide, and then I'm going to skip 2 chunks and then make another bar of 4, skip, and then another bar of 4. So on the x-axis, I have none, I have short, I have long. You'll notice a pattern if you've been watching me do this. In general, if it'll fit on my graph, I like my gaps between the bars to be about half the size of the bars themselves. My bars are 4 chunks wide. The gaps between them are 2 chunks wide. That's an aesthetics thing. As long as the bars don't touch, they're going to give you full credit. But as somebody who's been doing this a long time, that's generally a good rule of thumb. What goes on my Y? Relative frequency or percent. Good. I think 2 boxes is 10 is a good rule for this one. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Yeah. Tedious, yeah, because we're in statistics and sometimes it's tedious. But there wasn't any like calculations I had to go through, right? I just knew I needed to get up to 100, figure out how to fit it on my graph. Good. What's the next step? Step 4, draw the 100% bars. Another thing that's tedious, but not technically difficult. I'm just making each bar all the way up to 100. I am having difficulty making it perfectly straight because I'm drawing on a TV, which is difficult. These are your notes. I'm never going to see them, so if your lines are wavy, that's fine. If this is test day, what should you do? Very good. Gold stars to everyone. Rulers are your friend. All right, Samuel. What's step 5? You are not Samuel, but I appreciate your enthusiasm. Samuel, what's step 5? Segment them. Very good. And to segment them, I need to start doing calculations. Yeah? I am looking at conditionals where the variables on my x are my conditions. So I should have calculations for the none, calculations for the short, calculations for the long. And then I should have wins and losses. And for each of those wins and losses, for each column there, I should add up to 100 because I'm segmenting this way, dividing it into chunks. Yeah. All right. So I'm starting with the none column. The rest of the table doesn't exist. I am right here. In that column, how many wins? 7 out of how many total? 15. Very good. If we convert that to a percent, I got 47 rounded. I rounded to the nearest whole percentage to make it easy to graph. So fraction, move the decimal place twice, round it up or down. Good. Out of the nones, how many losses? 8 losses in the nones column out of 15 total games in the none column, which should be 53, even without a calculator, because those two numbers should add to what? 100. Very good. So my first bar in the table, the none bar, I'm going to segment. I need to ask myself a question. Do I want the wins on the bottom or the losses on the bottom? What's my lower segment going to be? The wins? Wins first. I heard wins first. So we're going to do the wins first. I'm going to color code. I'm going to make my wins red and my losses blue. And I'm going to put the wins on the bottom, meaning when I start at 0 and go up, I'm making a hash mark at 47 for the wins, which is right about here. That's my 47% marker. So wins is the lower 47%, which means the losses are the upper 53%. Yeah. Conditional probability, conditional relative frequency for each of the columns. I'm going to pop a couple minutes on the clock. I want you to fill out the rest of those conditional relative frequencies and get your bars segmented. Okay, those of you who've gotten through the conditional calculations, do we agree with my relative frequencies? You see nodding and thumbs up. Yay, good. Now we just got to slap them on the board. Wins on the bottom. So second segment, the wins go up to 52. Third segment, the wins go up to 63. Perfect timing. Huh? I did. Thank you. I appreciate that because usually I will forget. Do we see any patterns in this graph? I see some nodding. What was that, Ricardo? What's increasing? The win percentage is increasing. As I move from amount of rest category to the next category, the more rest I get, right? The further to the right I go on my graph, the larger the percentage of wins for that amount of rest. Yeah. So this tells me that there is likely a relationship between the amount of rest that our Golden State Warriors players get and the percentage of wins following that amount of rest. Yeah. Do I know 100% that it's a causal relationship? More rest will cause it? I see Ivan shaking his head no. Very good. We're going to talk more about this next time, but correlation or relationship does not imply causation. There is a very popular example of the number of movies that Nicolas Cage starred in a year and the number of drownings in pools that happen per year, and they correlate very strongly. More Nicolas Cage movies, more deaths in pools, less Nicolas Cage movies, less deaths in pools. I'm pretty sure that Nicolas Cage is not running around pushing people in their pools, right? There is a correlation. There is no causation there. So when we talk about relationships, and this is really important for the FRQs, you can state that there appears to be a relationship. Changes in one seem to happen when changes in another happen. You should not say one caused the other unless you have gone through the statistical evidence necessary to prove that. And that's a whole different discussion. So it is very important when you talk about relationships after graphing that you do not use cause, A caused B, or A proves B. Very conscious of the wording you're using. Okay, questions on a segmented bar graph. Okay, I'm going to go ahead and stop our notes here.